Right. Hi everyone, I'm Borcherding, the head of quantum software of QUDORA Technologies, and I'm here with a great team of quantum software engineers, namely Tobias Schmale, Mario Schulte, and Nico Tretschanke. Mr. Staufen here unfortunately cannot be here today. Let me just say a few words about QUDORA Technologies, because probably not all of you have heard of this company before. It was founded in 2021, and it has its roots in the Quantum Valley, Lower Saxony, which is the northern Quantum Valley of Germany. And the company really took off in 2022 when we won a major project from the German Aerospace Center, the DLR, for which we're building a 50-qubit trapped ion quantum computer now. And our goals in this project are really ambitious. We try to make this Germany's best quantum computer. And today we're here with the software team, and we're thrilled to announce that our QUDORA Cloud platform is now publicly available. And the future of the upcoming quantum computers of QUDORA and its partners will be accessible through this platform. But you can already register today and upload your hybrid quantum classical algorithms to it, and they will be run by our emulator, which is based on a real noise model of a trapped ion chip. We support OpenQASM2, discrete dynamic circuits, and QIR uploads. And yeah, if you'd like to learn more about QUDORA, our cloud platform, or just want to have a chat about QIR and related software tools, then visit us at our poster. Thank you.
So next one is Laurent.
Hello, so I'm from Alice&Bob, and there is a little lie, I'm not Laurent, I'm Eli, but we had a last minute change. So Alice&Bob, we are trying to build a quantum computer based on cat qubits. The idea of cat qubits is that you use a bosonic code to suppress the bit flip noise at the qubit level. And so you are left with the phase flip noise to correct, so that would allow to reduce a lot the overhead of error correction by having, for instance, a repetition code instead of a surface code. Of course, we have now other architectures based on DPC code. And so the software we have...
You say click, I can.
So we have several pieces of software that the poster present. So first one here is the software to actually access just the chip. So we have one qubit available on the cloud. So if you want to play with it, that's the software you have to use. You won't run huge algorithms with one qubit, but you can check yourself the noise properties of this qubit. That's the point of this software. Then another piece is to simulate what would be the logical qubit with their noise. So if you want to test some algorithm and its resilience towards the noise that we expect at the logical level, that's what we want to use. So it's implemented as a backend on top of Qiskit. And then the third part that we have here is resource estimation. So we worked with Microsoft to adapt the Microsoft resource estimator to be able to take cat qubits with repetition code into consideration. So now we have this working. So if you already know your number of logical qubits, CNOT gate, Toffoli gate, and want to know the overhead of error correction, that's the tool. And there is a last one that is not here, not really part of Felis, but independent, is dynamics. You can see it as a re-implementation of Qtip on top of JAX with auto-differentiable capabilities and possibility to run it on GPUs.
Good, thank you. Next one is, I'm saying maybe the evaluation Quantinuum is next.
Hello.
And just say click when I should.
Nice. Hello, my name is Vanya, and I'm here to represent Quantinuum NEXUS, which is our web platform for full-stack quantum computing. If you don't know Quantinuum, we make trapped ion quantum hardware and lots of different types of quantum software. NEXUS is available through a website, through an API and a Python client, and aims to bring all that together and give it to people so they can do cool science. Click, please. So, yeah, NEXUS presents a uniform interface to access not only our trapped ion quantum hardware, also hardware by the vendors such as AWS Bracket and IBM Q, And indeed, we offered lots of different types of managed compute. Not only our Ticket, next generation quantum compiler tools, Quanto, our quantum chemistry toolkit, and our configurable emulator for our own hardware. We focus a lot on data storage, and offering that is a useful way, useful tool for scientists. To that end, we have a lot of secure data storage with access control, useful collaboration features so that you can work with researchers and research groups in other organizations. And indeed, we want to give you the ability to structure, query, and filter your data using useful programmatic and API tools, so you don't have to worry so much about maintaining massive file systems of data and doing string parsing, massive string concatenated file names, which is tends to be what people do. So NEXUS is going to be publicly launched next month. We've been working with a lot of great research groups in the industry and academia for the last year. They've done a lot of really cool work on NEXUS. If you would like to register yourself for interest or access, use that QR code or come up to the poster, talk to me afterwards. Thank you very much.
Thank you. Next one is from Pasqal.
Yeah, thanks a lot. So my name is João. I work at Pasqal in the Quantum Libraries team. I'm here to talk to you a bit about Qadence. So it's an open source tool that you can use today. It has a big focus on differentiable and also combining digital and analog programs. So a few interesting things that we implemented in Qadence, you can see there on the architecture scheme. So when you define a register of qubits, you can also give it a topology. So this is very inspired by the way that neutral atom technology works. This topology you can then use in your program, for example, in the way that you define your analog blocks. So the blocks go into this block system of operations that you can combine both digital blocks, analog blocks, and everything seamlessly combines together in your program. And then in terms of differentiation, you can arbitrarily compose parameter expressions through an integration with SymPy as well, and combine those into your block program in any way that you want, either as parameters to your digital gates or maybe as coefficients in your Hamiltonian for your analog operations. So in terms of differentiation, this Qadence integrates with PyTorch. And so in terms of the way that you can pick different differentiation modes, then Qadence utilizes the PyTorch framework to, for example, change the differentiation function that is used by the computational graph. So you can, of course, use auto-differentiation by the PyTorch itself, or you can use, for example, parameter shift rules that will then be automatically picked up by the runtime and the optimizer to run your program. So yeah, this is just a few examples, but please come check out our poster if you'd like to discuss more. Thanks a lot.
Thank you. Next one is from Fraunhofer.
Yes, hi everyone. I'm Raphael, and I'm here to present Qrisp to you. What is Qrisp? It's a high-level programming language for quantum computers. And why do we need that? Programming with a circuit is super painful and non-scalable. Also non-modular and many other different problems. Why and how is it different? Our programs revolve around variables and functions and no more qubits and gates. And this way you can structure your code more and really get the most out of it. Furthermore, it also allows you to really think in quantum and less like someone that's just chaining together some unitary matrices. How can you try it? You simply execute the pip install command there and you immediately have it on your laptop. Okay, so now I want to go into some features. First of all, quantum typing. We have quantum types that allow you to structure your programming even more, and it simplifies many of your development aspects. Second, we have automatic uncomputation that allows you to automatically disentangle the variables that you programmed previously, and that also reduces the code size, but also like the mental load by a lot. Finally, we have an implementation of Prost algorithm. Of course, we also have other algorithms, but this one is particularly interesting because, as you can see, it's super short. It's like 11 lines of code. Yet it's super efficient. We benchmarked other open source implementations, and we found that ours is much more efficient. And yeah, basically, this concludes my presentation. Thank you.
Thank you. Next one is from the Software Competence Center in Hagenberg.
Thank you very much. My name is Stefan. I'm from the Software Competence Center in Hagenberg, a small village in Austria near Linz. And I'm here to present a poster together with my team, Vanya and Matthias, on quantum algorithm engineering. So, please, and 4 more, please. What we have found out working with companies that are interested in quantum computing from an industrial perspective is we have a lot of stuff going on the lower level hardware and lower level software, and a lot going on the use cases or perceived use cases that the companies want to pursue. Now, there's a lot of stuff missing in the middle, what we refer to as the gap, and what we are proposing to do with this project is to bridging this gap on particular spots that we find most promising. Please. So we have some core projects on combinatorial optimization because this has a wide applicability, and quantum machine learning, again, wide applicability, and it's a hot topic and lots of stuff going on. Also, this is framed by engineering aspects on quantum computing because we cannot get around that, and also software engineering because we have to develop the right tools to avoid having all the chasm style stuff. So to develop further what we've seen in the presentations today so far. And we can go into a little bit more detail, but I think we are already out of time, and I don't want to stress your attention when necessary. So please come to our poster, talk to us. If you're from a quantum company, let's talk about what we did right, what we could also adjust for the project. If you're from industry, what is interesting points for you. The project will not start until hopefully 2026, so we have time for talks right now, and hopefully can improve that. Thank you very much.
Thank you.
Hello everyone, my name is Eric. I work at Sanato, and I love compilers. I know you've heard a lot about compilers in the morning, so I'm not going to talk about performance or the hybrid program presentation. Instead, I'm going to talk about the plugin system. Imagine I'm a researcher in quantum compilation, and I have a transformation that will reduce the gate count of some possible set of circuits. And I publish my paper, and that's great, right? But I also want to make sure that people are using my transformation. Right now, what would you think you would need to do? Well, you need to implement your transformation perhaps on like IBM, Qiskit, or like CUDA or NLA. But in compilers, there's already this concept of plugins where you define your transformation, and it will take some representation as an input, you transform it, and then you return it as an output. And you can do it without modifying the main compiler. So you can do that on your own little shared library. Of course, so I think this is a good step in the right direction for making sure that your research reaches many platforms, but it's not the full story because there's not a lot of standardization yet. So yeah, hopefully this will help you reach out. Your work will reach more users. Thank you.
Thank you. And we continue with Joshka.
Hello everyone. I'm Joshka from the Quantum Software Lab in Edinburgh. And I'm here to add to my LTPC package, which is a software tool for the design and simulation of decoding algorithms for quantum encryption. So you can install the package right here, if installed on LTPC. And from there, you go from importing the package to decoding your favorite quantum encryption codes. So that's in 10 lines with our favorite programming language.
Okay, so the decoder is a critical part of any quantum arithmetic protocol. Specifically, it's a coprocessor that is designed to perform inference on measured syndromes and suggest suitable coders. So for many years, we've seen lots of software packages implementing decoders for the surface code. However, these decoders aren't very generalizable to broader families of quantum arithmetic codes. So the aim of our package is to provide a very general, flexible decoding solution. And specifically, we provide decoders that decode anything, whether they're structured or unstructured, so they're applicable to surface codes as well as more general quantum codes. So we do this by implementing decoders based on belief propagation, which is a very flexible algorithm commonly used in classical protocols such as 5G and Wi-Fi, and we augment these belief propagation decoders with quantum-specific modifications. The core algorithms are written in C++, but the front end is in Python, so it's easy to use. Here we have an example of some simulation that we're going to use using the package. Yeah, please scan the code, download the package, try it out, and talk with me at the post session. Thank you.
Now, Steph is next.
Hello.
Yeah, exactly. To put the microphone a bit closer to your mouth and talk about it.
Hello, I'm Vito from CDA-TUM. I'm here to present you Quantum and its capabilities. Quantum is a quantum circuit emulator based on tensor networks, which uses matrix product states and three tensor network to emulate very large quantum systems. It is optimized for high performance computing systems, and it's entirely written in Python, making it user friendly. And Quantum belongs to the Quantum T suite, where Quantum T stands for Quantum Tensor Network Emulator Applications. And what Quantum does is to harness the efficiency of quantum networks and the sparsity and entanglement properties of quantum states to emulate quantum systems with very large quantum systems with less memory with respect to other emulator methods. And today I'm here also to show you the results of Quantum we obtained benchmarking them on Leonardo supercomputer, which is hosted in Bologna and Tunica. We emulated the quantum Fourier transform applied to quantum volume random circuits, which is a very highly entanglement circuit, and we emulated it on using different settings. If you will come to see the poster, you will have the opportunity to see different comparison, how Quantum performs on different HPC settings, how the possibility to change, to create the maximum one dimension of the tensor networks allows us to reduce emulation times and also to emulate more than 50 qubits on one single CPU. You will have a possibility also to see a comparison with the Qrisp matrix product state emulator, and also a comparison between the use of different linear algebra mechanics modules which Quantum implements, which are TensorFlow, JAX, Torch, and NumPy. And this is a preview of one of the comparison I told you. So please come back to the first slide. I want to thank you for the attention. Scan the QR code if this presentation interested you, and I will wait for you at the poster area. Thank you.
Hello, my name is Willem de Kok. I'm from TNO, and I present to you QGIM. The godfather of QGIM is Sebastian Veld, who is also one of the panelists later on. And he had the idea of applying reinforcement learning techniques to do some of the compilation steps. So what we built was a GIM, a platform where you or other people can train reinforcement learning agents to do specific parts of the quantum compilation. It was Sebastian together with Stan, Tarek and me who built it, and we already had 2 master students who really trained agents and did some first benchmarking. Could you go to the next one? So you can just pip install it. It's on pip. Yes, next. So we focus on 3 passes, namely the initial mapping logical qubits from your quantum circuit to physical qubits on your hardware. Routing, basically placing swaps, and scheduling, so taking into account the clock times and which gates can be executed simultaneously or not. These are the three environments we built, and you can train on them. Next. So it's a gym. You have these three environments, which are your bench press, your squat rack, etc. And you can train with the method you like. We have some visualizations which help you to understand what happens and also to verify that it actually works. And what is reinforcement learning? It's basically, I thought of the road signs in the Netherlands. Once you're training, you get the response of either, nice, you're driving in the right speed, or you're driving too fast. Luckily, that doesn't happen on the German Autobahn. But in the Netherlands, we're a bit more precise. But that's what reinforcement learning is about. So these reward functions you can optimize yourself, or we also have some customary reward functions.
Thank you.
Yes. So hi, my name is Marius. I'm with the quantum computing team of Eviden, and I'm happy to present to you today Captiva, which is our quantum computing software framework. Go to the next slide exactly. So originally in 2016, Captiva was developed mainly with the intention of being an educational tool for people to teach them how to write code for quantum computers and also how to execute it and interpret the results. It now has actually emerged to a multifunctional quantum computing solution which covers everything from defining the algorithm to actually executing it on real hardware. There are a lot of building blocks coherently work together. On the one hand, we have our own quantum computing quantum programming language, which is compatible with most of the commonly used quantum programming languages. We have a lot of inbuilt libraries which cover common use cases in different quantum computing approaches like gate-based, annealing, and analog. Then on a lower level, we also have a toolbox to prepare your algorithms for running on the real hardware, so optimize circuits, compiling them, and in the end, we also include very powerful simulators to execute the algorithms and get results in the end. And if you don't want to run it on a simulator, but instead run it on a real hardware, you can also very natively integrate a real GPU, either as a service or on-premise. That is not only presented on an abstract level, we also have real applications on our posters where we use Captiva in some projects. So come over to our poster, my colleagues Stefan and Michael are also here, and we can show you the results and the applications and we can discuss about it. Thanks.
Oliver.
Oh, so some of you already know me, but for anyone who doesn't, my name is Oliver. I'm a Chancellor's Fellow at EPCC, the University of Edinburgh Supercomputing Centre. And what I'd like to talk to you about today is CQ, the specification for C-like interfaces to quantum computers. I'm very fortunate that Bettina has already given her talk today, because that means I can explain CQ in the following way. CQ is for people who really like QUDORA, but think C++ is just a bit too high level. So, if that is you, let's talk about CQ. Bettina mentioned all the nice things you can do with memory management in C++ and things being deallocated for you. In CQ, you have to do all that yourself. That's by design. So it's really about talking to a classical coprocessor that is glued to a quantum computer. How would I manage that interface? Now, the important question you may be asking yourself at this point is why on earth would anyone in their right mind want or need such a thing? And the answer is that what we notice at EPCC is that most of our users are still using Fortran. So, the question I ask myself as a researcher in a HPC center is, how am I going to help people who are using Fortran eventually take advantage of a quantum computer? Now, I am not going to advocate for writing a Fortran interface, however, C is a nice medium of exchange through which we may be able to do such a thing that I can just about tolerate. So, if you'd like to learn more or just discuss data synchronization between classical processors, please come and find me at the poster or I'm around for 2 days. Thank you.
Thank you. And we've got Michael.
All right, great. Hi everyone, a pleasure to be here today. I'm Michael, co-founder and CEO of Aquarius. We're a team of over 30 quantum experts and a spin-off from the LMU University here in Munich, leveraging almost a decade of experience in building quantum applications across various industries. At Aquarius, we focus on quantum computing for real-world applications. And today I'm excited to introduce you to Luna, our platform that makes quantum computing accessible and practical for end users. So let's dive right into how it works. Our platform consists of 3 core services. First, we have LunaSolve, our service designed to handle large-scale optimization problems. LunaSolve lets you upload your own problem or choose from our library of over 40 pre-built use cases, automatically transforming your data into a format that's compatible with all of our over 30 algorithms. No need to even build your own quantum model. With its AI-driven recommendation engine, LunaSolve selects the optimal approach and runs it on the most suitable hardware, delivering fast and actionable results without requiring in-depth expertise. But for our quantum experts here, of course, all encodings, algorithms, and backends are fully customizable, allowing you to adjust the pipeline to meet your specific needs. Next, we have LunaBench, our framework that lets you benchmark algorithms with just one click. You upload your dataset, choose the desired algorithms and backends, and with a single click, the entire benchmarking process is automated. So you can go grab a coffee, and when you come back, all your results are neatly organized, complete with detailed visualizations and metrics. LunaBench also integrates with all of LunaSolve's algorithms and backends, and allows you to, of course, upload your custom data, but also add custom algorithms and backends. So LunaBench saves you time by automating the very laborious and error-prone process of building benchmarking pipelines, especially when working with multiple quantum backends. Instead, you can focus on what really matters, your benchmarks. And finally, there's LunaQ, our tool for quantum engineers. So LunaQ provides access to various quantum hardware systems, including superconducting circuits, neutral atoms, or trapped ions. It handles the complexity of integrating various frameworks and APIs, and makes it easier for you to run your quantum circuits across various backends. So instead of navigating this very complex landscape on your own, LunaQ takes care of it for you. We go to the next slide. Perfect. So after successful beta phase, Luna will officially publicly launch on November 4th, empowering developers working on life-saving medicines, efficient supply chains, or sustainable energy solutions. You can register today at aquarius.com to secure access with options for academic and enterprise licenses, as well as a free tier at no cost at all. And we're hosting a Go Live event on launch day, where I'd be very happy to invite you to join as long as slots are available. Just reach out to me afterwards. Thank you for your attention.
Hello, I am Thierry from INRIA, and I'm happy to present you graphics. So it's a library we developed in Python for compiling and simulating MBQC models, so measurement-based quantum computing. It's a joint work with the Oxford University and the Tokyo University. And so MBQC has proven to be useful for photonic machines, for verified blind computing that allows us to use cloud to delegate computation without revealing anything about the computation. And it's close to the ZX graph language, which can be useful for optimizing as intermediate language for optimizing circuits. So mainly, so graphics provide representation and intermediate language representation for patterns, Python. And those patterns can be obtained by transpiling from circuit or from ZX diagrams. And we can find reason on these patterns for optimizing them for signal shifting to pre-simulate all the polling measurements or to minimize resources like minimizing the width of the simulation of the text. And then we can use these patterns to do some visualization for debugging purposes or to understand more things about the circuits, or we can simulate them with some standard simulators like state vector or density matrix for noise simulation. And we can even train the patterns on real machines with Qiskit or Perceval for photonic machines. And I will be happy to discuss about that on the poster, and then you can even fit install the graphics.
Cool, thanks a lot.
Hi, yeah, so I'm Marco. I'm at Newcastle University, although I'm moving to Paris basically next week. So I'm going to talk about a little bit about formal verification. So with Pasqal programs, generally you want to check that your programs behave the way that you do, and so we should really want something similar for quantum programs as well. And so along those lines, there are various different techniques out there for going about verifying your programs, but a lot of those approaches are manuals, and that makes it very difficult for developers to actually use them. So that's why I've been mainly looking at automated ways of being able to verify programs and other aspects of the quantum stack. And next slide, please. And so this is why I've been developing Silver, or Silver verification. And essentially, you take in a Silver program, which is a high-level quantum programming language, and then you go through this sort of flow of giving in your specification and then turning it into an intermediary model, which you then can send off to an automated tool known as an SMT solver, which works with SAT plus some theory on top of it. And then that will automatically check if your behaviors are being met by your program. I'm developing this. I'm planning on continuing development of this. So if anyone's interested in talking about formal verification and how it can be applied, not just at the program level, but at different levels of the quantum stack, then please do come talk to me at my place.
Cool, thank you. Next. Oh, I'm sorry. Oh. Here you go.
It's very funny that we are in Germany. Majority of us, English is not our first language, but we communicate in English. Does it mean English is the best language?
Better than German, I would say.
My name is Pasqal. I am Director of Academic Innovation at Wolfram Research, and we are among those companies who wants to make everything computational. And by everything, I mean literally everything, from weather data to geodata to quantum, all the way to whatever you have in your phone. We are a functional programming language, which is completely different from majority of programming languages that you guys know. Most people, they know procedural programming language, and sadly, many students nowadays, they have no idea that there are two big paradigms in programming languages, and one of them is functional. And I think, at the university, we should do a better job exposing our students to functional programming language. So, what is special about our product is it can do many different things, but the punchline is symbolic computation. What is a symbolic computation? Let's say that whatever you learn at your calculus courses, doing an integral, I don't know, the integration of sine x dx, and the interval is from a to b. What's the result? Negative, cosine b plus cosine a. That's what we call as symbolic computation. And we are among a few platforms in the world that we can do symbolic in every possible way. Literally, quantum, non-quantum, geo, weather data, image processing. So last 3 years, can we go to the next slide, me and my team, we built a very small quantum group at Wolfram Research, and we developed lots of functionality to do quantum computation. We inherited everything from Mathematica. Because of that, we can do symbolic. We can do lots of other things, for example, for us, it doesn't matter if you have analog or digital quantum processing unit, for us, it's the same thing, because we see everything the same. Because of that, we can do a lot. So our story of a framework is not just about quantum computing, it can be about quantum sensing, quantum communication, quantum annealing, practically everything with the name tag quantum. I'm going to claim even quantum gravity. Somebody asked me on LinkedIn, does it include the idea of quantum gravity? Yes, we'll be surprised that we can include quantum gravity. But anyhow, I'm here together with Armin and Harry. Please, find us. and ask us any question that you want. And I would be more than happy to convert you from any programming religion that you belong to. Thank you.
Then we got last page. The last one, sorry. Yeah, like, sorry. Here you go.
Hi everyone, I'm Asmar Bukid. I'm a PhD student at Simula Research Lab. And in Simula, we focus on quantum software development, particularly topics of AI for quantum software engineering, quantum software applications for classical software engineering, and quantum software testing. So when we talk about quantum software development, it requires reliable program execution in different stages. And when we talk about the natural workflow of the current software technologies, we have the quantum hardware where we get the raw results. Depending on the problem we try to solve, we are either using an estimator type of interface or a sampler-based interface. And we see that for estimator type of interface, there are many error mitigation methods that are available that you can utilize in your frameworks. But we noticed that for sampler type of methods, there are not many tools available that allows seamless integration across different frameworks. So here we developed our own tool, QUDORA, which is based on a REST API that allows you to do error mitigation on raw distribution outputs. And there's a link for the YouTube video demo and also a GitHub link. And for QUDORA, there's currently one algorithm implemented in it, but we are hoping to implement a lot more algorithms in it. And we hope that if you can convert your circuit to an open representation and you know how to use HTTP requests, you should be able to integrate QUDORA in all of your workflows. Thank you.
Really cool, thanks. Now we discuss.
Now it's me, yes. Yeah, so suppose you want to create a quantum state for classical data. That could happen, for example, if you do chemical computations here, and suppose you don't want to start with your Hartree-Fock approximation, which is quite simple. Also may not provide all the advantages. Now, if you go a little bit more deeper into approximations, for example, DMRG or NPS states, they're not as trivial and maybe not as sparse potentially, so you need to have some sort of solution how to actually code it into an efficient way. Usually when you work on molecules, what you do, you have to have many configurations that you test out, and you have to repeat those experiments often, and actually in the same way you have to often create these quantum states. Now, usually you don't have the time to handcraft these circuits. That's why you want to have an automated system. And also the other thing that you don't want to have is circuits that are too long. That's also my question to Yehuda previously. So, what to do? This is where QAlchemy comes up into the picture, and we create these classical data into quantum circuits. And one of the nice features that we have here is that you can actually have a lot shorter circuits by a tunable fidelity loss. That's why my question was there in the previous talk with Yehuda. All right, and this you can see this advantage here quite strikingly on the plot that you have down here. On the x-axis, you have the fidelity loss. On the y-axis, you have the CX gates, the number of them. And if you take a fidelity loss, you can quickly decay the number of CX gates. You know that as well. Yes, and it's actually a power law, and have the equation up here. So what this really helps you is to gauge the way and go into your hardware and what the coherence times are and the noise level. Next slide, please. That's why we also say reduce the quality to fit NIST. That's one part that you could do. And I also want to show you a very visual example here of this data set. This is the MNIST 784 data set. It's a 28 by 28 grayscale pixels, handwritten digits. And we applied QAlchemy on each of them, ranging from a fidelity loss of 0.0, which is low loss on the left side, all the way down to 0.2. And the numbers are a bit small, of course, but you can see that the CX gates really rapidly decay, while the quality of the pictures don't really matter so much. I mean, you can see it's in the dots here. Okay, the other advantage is you can automate your system, and we have a ready-to-use API. And within Python SDK, we have integrations with Qiskit and Petaling. And if you don't like either of them, you can just use the Quasm 2.0 backend and use it as well. The access is free up to 12 qubits. Yeah, that's about it. And I'm pleased
scan the code here, sign up today, try it out. Thank you very much.
Thank you. Florian.
Hello, I'm Florian from Fraunhofer IAO Stuttgart, precisely, and I'm going to talk about a framework called QUDORA Cloud, which is joint work by Fraunhofer IAO and Fraunhofer FOKUS in Stuttgart and and it came out of a public project from the German Federal Ministry of Economics and published together with So, QUDORA Cloud. The idea is to make quantum machine learning, which is quite complicated, more accessible to these anti-barriers. Next slide. So this is a machine learning pipeline. Forget about the queue for a moment. Yeah? Already machine learning is quite complicated. So imagine you're a domain expert on, I don't know, giraffes and life. Pictures of giraffes and life, you label them, and you don't want to care about it. This should be classified by a random forest or a support vector machine. You want to give this to your framework. And this framework should choose the best model and also train the best model for you. Basically, take a lot of models, train each of them, and by some benchmark, choose the best one for you. So this already existed, like in AutoML, Q in AutoML, so QML techniques. So like I said, AutoML facilitates all the tedious things you have to do in machine learning, next thing, and we put the Q in there. So we integrate the state-of-the-art methods in this hardware, and basically implemented supervised machine learning. Next year. So like I said, we can do reinforcement learning, but we can do supervised learning, classification, regression. We support IBM and AWS backends, also simulators, extendable, fine plates, and it says Q4, but it will be available in December. And I didn't push the QR code, but happily put at the visible link. Thank you very much.
Thank you. Next is Nicola.
Hello, my name is Nicola. I'm co-founder and CTO of Haiku, a quantum middleware company with the goal of making near-term quantum computers usable. While we are building our larger scale middleware, we also build tools which help us to achieve this goal. And today we're actually presenting the Revit. This is an open source transpiler which helps to optimize a number of quantum computing workflows. So imagine you need to do a classical shadows protocol. So today we heard a lot about transpilation and how important it is to optimize a number of gates in your circuits, but transpilation also has time complexity, and it often takes a lot of time if you want to do something like classical shadows, where you need to retranspile a lot of circuits for different basis sets as you do your tomography. So if you do it naively, you very quickly realize that even for 8 qubits, you need to wait for many hours to get the result. Probably you can go to the next slide. With Revit, you can do that much faster and much more efficiently. It's actually built on other tools and other components. You can combine here your favorite transpiler like Qiskit or TCAT, Xbiscuit, and you can also implement your own transpiler if you want. But it allows you to do this sub-circuit stitching and matching of different parts of your algorithm. And it allows you to do this different paradigm of transpilation, but you want to do many transpilations before you run something on the quantum hardware. And in result, it achieves us to shrink this time for a classical shadows from many hours to actually just few minutes. And it's also very useful for workflows like QML. So here's another example where you do a layer-wise training, and you can also shrink it from 2 hours to just like 20 minutes if you train this system. So very glad to talk to you. Approach our poster and see you then.
Thank you. Any more to come? There's Eric.
Hello everyone, I'm Eric, and I want to present you an optimization algorithm we developed. We call it excitation solve. and it can be used to optimize VQE circuits that are composed of excitations. So, for example, fermionic excitations, qubit excitations, or any other kind of excitations. And so this optimizer can globally optimize each parameter in your circuit. So you have different excitations in your circuit, and each excitation has one specific parameter. And we can optimize this parameter globally to its global optimum with this optimizer, and with the same cost as we do one gradient descent step. And next slide, please. And we tried this for different molecules for the UCCSD ansatz. So these are H2, H3+, lithium hydride, and water molecule in their equilibrium geometry. And we compared this to different state-of-the-art optimizers like BFGS in brown or Cobila in purple. And our optimizer is in red, in dark red, and in light red. And next slide. Yeah. Oh. Okay. So as you see, we outperform every optimizer for every molecule we benchmarked, and for H2 we are done in one VQE step, and for H3+, we can also be done in one VQE step if we use our 2D optimization, so we optimize two parameters at once. And for lithium hydride and H2O, you also see that we significantly outperform all the other optimizers. We benchmark this also for depth VQE, we benchmark this for also different bond distances for all these molecules. We did shot noise simulations, and you can check this out in our archive preprint. And as we discovered, you must use excitation sort for your VQE based circuits if you use excitations. And check out our poster. I'll catch you at my poster, and check out the preprint. Thank you. Thank you.
Hello, I'm Kenny Yang from QNASYS. We are a startup, quantum software startup from Japan. So today we would like to introduce our open source SDK, QD parts, and QD SDKs. So kind of the QD parts is already open, so kind of you can access from this QR code. So this is quite simple framework we developed, and it focuses on modular library and platform agnostics, and kind of above all, we really focus on the high performance of this. So kind of we understand some cases it's kind of slow, and kind of others kind of this is like we have our own benchmarks, and kind of it's like the 5 times faster than PyTicket and 10 times faster than Pennynail. So kind of if you are keen to some speed for the quantum software library, please access this QD parts. Like the inside, like we use the Rust and to speed up that. And kind of today we would like to more focus on the QD algo and QD VM, which stands for the virtual machine. So kind of this is unfortunately haven't opened yet. So we will open this next Monday. So kind of stay tuned for the next Monday. So kind of QD algo is like basically we have a lot of algorithms implemented here. So kind of for example for chemistry, there's VQE and quantum selected CI and other like the phase estimation algorithms, and also some early FTQC algorithms like the statistical phase estimation. So kind of that is chemistry, and more on CA and the optimization algorithms is coming. And kind of apart from that is like we are developing like virtual machines. So kind of today we don't have the full FTQC running, but kind of we can develop the virtual machine and kind of they do resource estimation and of the algorithm. So that is what this VM for. So next, please. And give you some example for this QD algo. So kind of maybe just giving the example here. So this is like some benchmark we took using this QD algo. So the left side is the number of the shots, and the right side is the execution time. And this is role is like we assume the fidelity of the hardware devices. So kind of the top is 10 to the minus 3 error rate device, and the bottom is a 10 to the minus 5 error rate. So kind of this green line is like VQE result. So if you have more shot, the accuracy is getting better, but kind of it will kind of never get chemical accuracy, unfortunately. So what we are focusing these days is like some statistical phase estimation techniques. So kind of also it's saying like if we have like low fidelity devices, you can it's kind of worse than the VQ result, but kind of if you have the better devices, you can see it's almost reaching the chemical accuracy. So kind of this kind of the benchmark you can using our the QA SDKs. Thank you.
Thank you. Certainly not East Holland.
Yeah, so my name is Roland de Hove. I'm very happy to have the last talk before the break, and I still have your attention. So yeah, I'm here to talk about PERT-US today, which is an operating system for quantum computers. So yeah, we developed it at PERT-QC. It's a company in Innsbruck and also in Hamburg. So the main idea. The main idea you see here on the right is this kind of framework of going from a real-world problem. In many cases, what we're considering now are optimization problems. And then it can go through this pipeline that we're developing, which is based on the parity transformation. So the parity transformation is a specific idea to basically transform the optimization problem into a different problem, solving the connectivity issue of the hardware. So the problem may need these connections that are not on the hardware. And so you have a qubit overhead in this transformation, but it allows you to make all the connections local, and also to make the circuit depth limited, actually constant for any system size. And so the parity transformation is the first step. Then we have specific algorithms for digital and analog. So for the moment, focusing on variational quantum algorithms and quantum annealing mostly. But we're also there looking to the future with fault-tolerant quantum computing. And then the next step is a hardware design optimizer. So here, it depends a bit on the user, where they want to run their algorithm. So there are, of course, a lot of tools available for hardware optimizers. So there we kind of connect to what users need. And so we would, for example, output in OpenQASM, Qiskit, or Cirq, a circuit that then the users can run. And so this parity architecture is kind of the core idea of the company, and there's many ideas that spun out from that. For example, also a specific hardware design that exactly fits this transformation of the optimization problem. If you can do these interactions on your device natively, then that would really synergize nicely with the architecture. And so a few of the highlights on our poster are then the PERT-QC architecture. So it's basically a mathematical transformation where we're happy to tell you more about. And then on the poster are some specific parity compilation algorithms that we published over the last years, as well as something I want to focus on, this swap test implementation of quantum algorithms. So it turns out that even if you have just a linear chain as your device, you can still do many algorithms without swap gates. And the basic idea is there to use the C-nodes to transfer the quantum information instead of using a full swap gate, which would take 3 C-nodes. So this offers a nice advantage over competing implementations in terms of C-node count. So we also have ideas of how to make universal quantum computing, and a project related to solution paths for quantum computers, which is about finding the best hardware and algorithms for a specific optimization problem, both based on the parity approach, but also looking at other approaches. Yeah, that's it. Thank you.